Hello everybody, welcome into another lesson. So today we are going to talk about the fundamental theorem of algebra. And the fundamental theorem of algebra tells us that a polynomial of degree n has n solutions in the complex number system. So in short, what this means is that the degree of your polynomial indicates the number of solutions you'll have in the complex number system. It does not mean that they're all going to be real solutions. Notice it says complex, which would include imaginary solutions. So you should, if for example, if you have a second degree polynomial, or a quadratic in other words, you should have two solutions in the complex number system. If it's third degree, you'll have three. If it's fifth degree, you'll have five, and so on. And repeated zeros count as, so if I had x minus 1 squared, well x equals 1, that x equals 1 would count as two of the zeros. Repeated zeros do count as part of your zeros. You don't only count it once, it would actually count for more than one if it's repeated. So let's get into some examples here. Let's actually start with the sum of two squares. So we have x squared plus 25. So you're given x squared plus 25. Now, when we were only considering the real numbers, there would be nothing we could do with this. But we're going to solve this. So x squared plus 25, you could take x squared, set that equal to negative 25, which would mean that x equals both plus and minus the square root of negative 25, which would mean that x equals plus and minus 5i. So those would be your solutions for x, and then what we're also going to do today is write our polynomial as a product of linear factors. So we can write this as a product of x plus 5i times x minus 5i. So a sum of two squares is factorable over the complex number system. It's not factorable over the real number system, but it's factorable over the complex number system. It breaks down into x plus 5i times x minus 5i. Going to have a similar one here. So let's say we have f of x equals x squared plus 36. So f of x equals x squared plus 36. Well, set that x squared plus 36 equal to 0. You have another sum of two squares. So this would turn into x squared equals negative 36. Which would give you that x equals plus and minus the square root of negative 36, which would give you that x equals plus and minus 6i. So there's your solutions for x. You have two solutions because it's quadratic. According to the fundamental theorem of algebra, you do have two solutions in the complex number system. In this case, they're both imaginary. Now you can factor this into a product of linear factors, which would end up being f of x equals x plus 6i times x minus 6i. That would be your factorization for the sum of these two squares. All right, f of x equals 16x to the fourth minus 81. So f of x equals 16x to the fourth minus 81. Well, this is about to get very interesting. So go ahead and set your 16x to the fourth minus 81 equal to 0. So this is a fourth degree polynomial, which tells you that you should have 4 solutions in the complex number system. Well, let's factor 16x to the fourth minus 81. We definitely have a difference of 2 squares. So this would factor into 4x squared plus 9 times 4x squared minus 9 equals 0. Now, you have a sum of 2 squares and a difference of 2 squares as your factor. Well, we can break this down further. That sum of 2 squares, that 4x squared plus 9 would turn into 2x plus 3i times 2x minus 3i. And then that 4x squared minus 9, that would turn into 2x plus 3 times 2x minus 3 equals 0. So there's your 4 solutions. So if you set each of these equal to 0, you would get 2x equals negative 3i, which would give you x equals negative 3 halves I. 2x minus 3i equal to 0 would give you 2x equals positive 3i. X would equal positive 3 halves I. 2x plus 3 equals 0. You get 2x equals negative 3. X would equal negative 3 halves. And then 2x minus 3 equals 0. So you would get 2x equals 3. So x would equal 3 halves. So these are your 4 complex solutions to this polynomial. So you have 2 reals and 2 imaginaries. So this further proves the point of the fundamental theorem of algebra. Now we can write that function as the product of linear factors. This would be f of x equals 2x plus 3i times 2x minus 3i times 2x plus 3 times 2x minus 3. So that's how you would write this exact same function as a product of linear factors. Do one more like this, then we'll move on to some other stuff. Alright, so we have f of x equals 81x to the fourth minus 625. So we're given f of x equals 81x to the fourth minus 625. Okay, well, this definitely starts out as a difference of 2 squares, so set that 81 x to the fourth minus 625 equal to 0. That factors as a difference of 2 squares, so this will become 9x squared plus 25 times 9x squared minus 25 equals 0. So you have 2 factors, one of which is a sum of 2 squares, one of which is a difference of 2 squares. So that 9x squared plus 25 would factor into 3x plus 5i times 3x minus 5i. Then that 9x squared minus 25 would factor into 3x plus 5 times 3x minus 5. All that would equal 0. Now you just set each of your factors equal to 0. So 3x would equal negative 5i, which means x equals negative 5/3 I. And then 3x minus 5i equals 0, so 3x equals positive 5i. X would equal 5/3 I. 3x plus 5 equals 0, so 3x equals negative 5, x equals negative 5/3, and then 3x minus 5 equals 0, so 3x equals 5, so x would equal 5/3. So you have 4 solutions again in the complex number system. You have 2 imaginaries and 2 reals. For your solutions, you get x equals both plus and minus 5/3 I, and then plus and minus 5/3. And then we can write this function as a product of linear factors. So f of x would equal that 3x plus 5i times 3x minus 5i times 3x plus 5 times 3x minus 5. So that's how you would write this as a product of linear factors. All right, let's step this up a little bit. So we have f of x equals x squared minus 14x plus 46. Well, clearly this is not factorable. So we can use one of 2 methods to solve for x. We can either use completing the square or we can use the quadratic formula. Personally, I would prefer we could use completing the square because we have even numbers, which will make completing the square a lot easier. So let's take that x squared minus 14x plus 46 and set that equal to 0. So the degree of the polynomial is 2. That tells us we should have 2 solutions in the complex number system. Whether they're real or imaginary, we don't know yet, but we will have 2 solutions in the complex number system. So let's complete the square. So this would turn into x squared minus 14x. All right, so then that would be plus 49. Would end up equaling negative 46 plus 49. So, and then in this case, you would end up getting x minus 7 squared equals 3. So then x minus 7 equals plus and minus the square root of 3. So that would give you that x equals 7 plus and minus the square root of 3. So in this case, we had 2 real solutions. It worked out where both of our solutions were real. X equals 7 plus and minus the square root of 3, which it's still complex because real numbers are part of the complex number system, but now we need to figure out how to write this in the form of a linear factorization. So f of x is going to equal, of course, x plus. Now in this case, so you have 7 plus the square root of 3, and then you have 7 minus the square root of 3 for your 2 zeros. So that means this for 7 plus the square root of 3, this would turn into f of x equals x minus 7 minus the square root of 3 times the quantity of x minus 7 plus the square root of 3. That's how you would write something like that in terms of linear factors. F of x equals the quantity of x minus 7 minus the square root of 3 times the quantity of x minus 7 plus the square root of 3. So yeah, that one was a bit of a doozy. And I have a similar one to this. All right, f of x equals x squared minus 12x plus 34. All right, so f of x equals x squared minus 12x plus 34. Again, very clearly not going to factor, but I would say we can complete the square. So we're going to have, let's take x squared minus 12x plus 34, set that equal to 0. Well, a second degree polynomial tells us we should have two solutions in the complex number system. So let's complete the square. This would turn into x squared minus 12x plus 36 equals negative 34 plus 36. So this would factor into x minus 6 squared would equal 2. So then you'll end up getting x minus 6 equals plus and minus the square root of 2. So x equals both 6 plus and minus the square root of 2. Those would be your two solutions. And again, they both worked out to be real numbers this time. All right, so now we need to find the linear factorization. So f of x equals then the quantity of x minus 6 minus the square root of 2 times the quantity of x minus 6 plus the square root of 2. That would be your complete linear factorization of this polynomial. So yeah, it's a little bit hideous, but that's exactly how you would factor it. Now let's flip this around a little bit. Let's try to do one with an imaginary. We have x squared minus x plus 56. And you might be looking at this and thinking it's going to factor. 7 and 8 are factors of 56. Well, here's the thing. If you have both x plus 7 and x plus 8, you would get a positive 15x. If you had x minus 7 times x minus 8, you would still get that positive 56, but you would end up getting minus 15x. So this is actually not going to factor. And you could use completing the square, but you're going to have to deal with fractions. Do you really want to do that? It's actually probably best in this case we proceed with the quadratic formula. So let's take that x squared minus x plus 56, set that equal to 0. We should still have two solutions in the complex number system. So use the quadratic formula. X would equal that negative of negative 1, so that'd be positive 1 plus and minus the square root of that negative 1 squared minus 4 times that 1 times that positive 56 all over 2 times that 1, which would just be 2. So this would turn into 1 plus and minus the square root of 1 minus 224 all over 2, which would give you 1 plus and minus the square root of negative 223 all over 2. So now you probably see where this is headed. This is headed in the imaginary direction. And not sure if 223 factors. it definitely does not factor. I just checked. So this would turn into 1 plus and minus I times the square root of 223 all over 2. Those would be your two solutions for x. So yes, you've got indeed two solutions in the complex number system, and they're both imaginary this time. So we want to factor this as linear factors. Well, let's break this down. So that 1 plus or minus I times the square root of 223 over 2, this would break down into 1/2 plus I times the square root of 223 all over 2. It would also break down into 1/2 minus I times the square root of 223 over 2. From here, we can form our linear factors. So f of x would equal the quantity of x minus 1/2 minus I times the square root of 223 over 2. Now we're going to have another quantity times x minus 1/2, this time plus I times the square root of 223 over 2. So that one was a little bit messy, but there is your linear factorization for this particular function. Yowzer. All right. Let's move into higher than quadratic now. Let's use some of the other methods. So f of x equals 2x to the third minus 3x squared plus 8x minus 12. Well, we honestly don't really need to use synthetic division. If you look at this, f of x equals 2x to the third minus 3x squared plus 8x minus 12. So first of all, it's a degree 3 polynomial, which means we should have 3 zeros in the complex number system. If you look at this, we can actually factor by grouping. There's no need to break out synthetic division. So 2x to the third minus 3x squared plus 8x minus 12 is equal to 0. So factoring by grouping, this will turn into x squared times 2x minus 3 plus, for your 8x minus 12, you can factor out a common 4, then times 2x minus 3 equal to 0. So this would just factor into 2x minus 3 times x squared plus 4 equals 0. But that x squared plus 4 is the sum of two squares, so it'll factor further into the quantity of 2x minus 3 times x plus 2i times x minus 2i is equal to 0. Now we have three linear factors. So set 2x minus 3 equal to 0, you get 2x equals 3, x equals 3 halves, and then x plus 2i equals 0, so you get x equals negative 2i, x minus 2i equals 0, so then you get x equals positive 2i. So there's your three solutions. X equals positive 3 halves, and then both plus and minus 2i. So in this case, you had one real solution and two imaginaries for a total of 3 solutions in the complex number system. And here is your linear factorization right there for the function. So f of x would equal 2x minus 3 times the quantity of x plus 2i times the quantity of x minus 2i. There is your complete linear factorization of this function. So it's always nice when we don't have to use synthetic division. That sure does help. Alright, so let's see. We have another one here. 2x to the third minus 5x squared plus 18x minus 45. So f of x equals 2x to the third minus 5x squared plus 18x minus 45. Okay, well, we have a degree 3 polynomial, which means we should have 3 zeros in the complex number system. So if we look at this, once again, we really don't need to break out synthetic division. We can just factor this by grouping. So let's set this equal to 0. So you have 2x to the third minus 5x squared plus 18x minus 45 would be equal to 0. So factoring by grouping, this would break down into x squared times 2x minus 5 plus 9 times 2x minus 5 would equal 0. So this would then turn into 2x minus 5 quantity times x squared plus 9 quantity is equal to 0. Which now we have a sum of two squares, which will break down further into 2x minus 5 times x plus 3i times x minus 3i is equal to 0. So now you have your complete linear factorization, and we can set each of these factors equal to 0. So 2x minus 5 equals 0 would give you 2x equals 5. So x would equal 5 halves. X plus 3i equals 0 gives you x equals negative 3i. X minus 3i equals 0 gives you x equals positive 3i. So according to the fundamental theorem of algebra, this works. We have three solutions for a third degree polynomial equation. X equals 5 halves, then x equals both plus and minus 3i. And now we just write out the complete linear factorization for this. F of x equals 2x minus 5 times x plus 3i times x minus 3i. There's your complete linear factorization for this particular function. I have about 4 more. Unfortunately, these next couple aren't going to be quite as nice. So we have x to the third. So x to the third minus 11x plus 150. So yes, f of x equals x to the third minus 11x plus 150. Am I seeing that right? Yeah, it's just odd. Okay. Well, we have a third degree polynomial, which still tells us we should have 3 solutions in the complex number system. Well, it definitely isn't going to factor. Factoring isn't going to save us this time. We can't even use completing the square or the quadratic formula because this is not a second degree polynomial. we have no choice but to use the rational zero test and do synthetic division. So let's do our plus and minus p over plus and minus q. Well, the p is 150, so factors of that are plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 5, plus and minus 6. I want to say it actually does. Yeah, plus and minus 10. That'd be 15. Yeah, okay. So then plus and minus 15. Plus and minus 30. No, wait. Plus and minus 25. I almost forgot one. Plus and minus 25. Plus and minus 30. Plus and minus 50. Plus and minus 75. And then plus and minus 150. That would, of course, be all over plus and minus 1. So I think we have a good grasp on what our rational zeros are going to be. So now it's time to just start plugging away, see what we come up with. So let's do synthetic division. So coefficient of x to the third is 1, coefficient of x squared is 0, coefficient of x to the first is negative 11, the constant term is positive 150. Let's work backwards. Let's do positive 150. So let's bring down that 1. Okay, so 150 times 1 is 150. 0 plus 150 is 150. And we can clearly tell already we're going to be in the thousands and tens of thousands. This definitely isn't going to work. In fact, if I took negative 150, it would be pretty much the same thing. You would just be in the negative thousands. So we could definitely exclude 150s. You know, why don't we start with the lower numbers? Let's go with 1. Well, bring down your 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 11 plus 1 is negative 10. 1 times negative 10 is negative 10. 150 minus 10 is 140. We have a remainder of 140. That's not going to work. Unfortunately, with synthetic division, a lot of the time is trial and error until you get one that sticks. So this can be a bit of a doozy. Let's try negative 1. Alright, so bring down your 1 from above. Negative 1 times 1 is in fact negative 1. 0 minus 1 is negative 1. Negative 1 times negative 1 is positive 1. Negative 11 plus 1 is negative 10. Negative 1 times negative 10 is positive 10. 150 plus 10 is 160. Well, we have a remainder of 160. That's not going to work. So definitely our 1s are gone. Let's try 2. Alright, so bring down your 1. 2 times 1 is 2. Alright, so 0 plus 2 is 2. 2 times 2 is 4. Negative 11 plus 4 is negative 7. 2 times negative 7 is negative 14. 150 minus 14 is 136. Well, that remainder of 136 isn't doing us any favors, so that's not going to work. Let's try negative 2. So go ahead, bring down your 1. Alright, now negative 2 times 1 is negative 2. 0 minus 2, that is in fact negative 2. Negative 2 times negative 2 is positive 4. Negative 11 plus 4 is negative 7. Negative 2 times negative 7 is positive 14. 150 plus 14 is 164. So that's definitely not going to work. In fact, I would firmly believe we're probably going to have definitely higher numbers here. Your 2's are excluded now. What about 3? Alright, so let's try 3. Bring down your 1 from above. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. Negative 11 plus 9 is negative 2. 3 times negative 2 is negative 6. 150 minus 6 is 144. That's not going to help you. Alright, let's try negative 3 this time. So bring down your 1. Negative 3 times 1 is going to end up being negative 3. 0 minus 3 is negative 3. Okay. Negative 3 times negative 3 is positive 9. Negative 11 plus 9 is negative 2. Negative 3 times 2 is positive 6. 150 plus 6, that's 156. That's not working. So our factors of 3 definitely are not going to work. All right, let's try the 5's. Let's try 5. All right, so bring down your 1. 5 times 1 is 5. 0 plus 5 is in fact 5. 5 times 5 is 25. All right, negative 11 plus 25, that's positive 14. And then 5 times 14 is 70. 150 plus 70 is 220. Well, that remainder of 220 isn't going to help us. So let's try negative 5. So go ahead, bring down your 1. Negative 5 times 1, that's negative 5. 0 minus 5 is negative 5. Alright, so negative 5 times negative 5 is positive 25. Negative 11 plus 25 is positive 14. Negative 5 times 14 is negative 70. Well, 150 minus 70 is 80. Well, at least our remainder is getting smaller, but still we have a remainder, so that's the 5's are gone. That's just not going to work. Let's try 6. See if we get anywhere with that. Alright, so let's try 6 here. So bring down your 1. 6 times 1 is 6. Alright, now 0 plus 6 is 6. 6 times 6 is 36. Negative 11 plus 6 is in fact 25. 6 times 25 is 150. Well, 150 plus 150 is 300. That's definitely not going to work. Let's see if negative 6 works. I have a good feeling about this one. Let's see if negative 6 will actually finally free us from the misery. So bring down your 1. Negative 6 times 1 is actually negative 6. 0 minus 6 is negative 6. Negative 6 times negative 6 is positive 36. Alright, so negative 11 plus 36 is positive 25. Negative 6 times 25 is negative 150. Well, 150 minus 150 is 0. We found it. We found one of our zeros. Negative 6 was the winner. So now we end up having f of x equals x plus 6 times x squared minus 6x plus 25. So at least we got this down to a quadratic factor now, which is going to be so much nicer. So we want to take these factors, set them equal to 0. So we'll have x plus 6 times x squared minus 6x plus 25 equals 0. Well, that quadratic factor definitely isn't factoring, right? We're going to either have to complete the square or use the quadratic formula. Personally, I'm voting for completing the square. So set that x squared minus 6x plus 25 equal to 0. Complete the square, you would get x squared minus 6x plus 9 equals negative 25 plus 9. So this would turn into x minus 3 squared equals negative 16, which would give you x minus 3 equals plus and minus 4i. So you get x equals both 3 plus and minus 4i. So your linear factorization now, we can completely linearly factor this. You would end up having the quantity of x plus 6 times the quantity of x minus 3 minus 4i times x minus 3 plus 4i. So we got our linear factorization, and of course we just need to solve for the zeros. Just set each of your factors equal to 0. You get x equals negative 6 as well as 3 both plus and minus 4i. So those are all three solutions in the complex number system. F of x equals negative 6 and then both 3 plus and minus 4i. I have about 3 more problems, but they shouldn't be as bad as this one was. They shouldn't even be this bad this time around. All right. F of x equals x to the third plus 10x squared plus 33x plus 34. So we have another third degree polynomial, which tells us we should have 3 solutions in the complex number system. And this is not going to factor at all, so we have to use synthetic division in the rational zeros. So that p is plus and minus factors of 34, so plus and minus 1, plus and minus 2, plus and minus 17, and then plus and minus 34, all over plus and minus 1. So you only have 4 sets of factors to work through this time. Let's set up our synthetic division. Well, definitely going to say since every coefficient's positive, it's going to be a negative number that we divide by to make us have a remainder of 0. So that cuts our work in half for us. So coefficient of x to the third is 1, coefficient of x squared is 10, coefficient of x to the first is 33, constant is 34. Alright, let's try negative 1. So bring down your positive 1. Well, negative 1 times 1 is negative 1. 10 minus 1 is going to be 9. Negative 1 times 9 is going to be negative 9. 33 minus 9 is 24. Well, negative 1 times 24 is negative 24. 34 minus 24 is 10. We have a remainder of 10. That's definitely not going to work. So our 1's are gone. We've narrowed it down now a little bit more. Let's try -2. So go ahead, bring down your 1. Well, -2 times 1 is going to be -2. All right, so 10 minus 2 is going to end up being 8. -2 times 8 is -16. 33 minus 16, 17. -2 times 17 is going to be -34. 34 minus 34 is 0. So immediately we found the factor. Pretty much immediately. This will start to factor into f of x equals x plus 2 times x squared plus 8x plus 17. Well, that quadratic factor definitely won't factor any further, will it? But we can definitely use completing the square to solve for this. So let's take that x squared plus 8x plus 17, set that equal to 0. Completing the square would end up giving us x squared plus 8x plus 16 is equal to -17 plus 16. So this would factor into x plus 4 squared would equal -1. So x plus 4 equals plus and minus I. X would equal -4 plus and minus I. Now we can at least start forming the complete linear factorization. So f of x would equal the quantity of x plus 2 times the quantity of x plus 4 plus I times the quantity of x plus 4 minus I. There's the complete linear factorization of this function, and now we just list the solutions. So x would equal -2, and then it would also equal -4 plus and minus I. Those are all three solutions in the complex number system. I got two more, and they're going to be fourth degree. So we've elevated the degree one more time. So let's do a couple fourth degree equations. Or functions, I should say. No, let's just do 1/4 degree. I think you kind of get the idea, but yeah, like this one. So x to the 4th minus 8x to the 3rd plus 17x squared minus 8x plus 16. Well, none of this is factoring, that's for sure. And this is a fourth degree polynomial, which tells us we should have 4 zeros in the complex number system. So we're going to have to do the rational zero test and break out factoring. So that p are the factors of 16, so plus and minus 1, plus and minus 2, plus and minus 4, plus and minus 8, and then plus and minus 16. All over factors of 1, which would just leave these. So we have a little bit to work through here. So let's do synthetic division. So x to the 4th coefficient is 1, x to the 3rd is 8, x squared is 17. I'm sorry, x to the 3rd was -8, x squared is 17, x to the 1st is also -8, constant term is 16. Let's start with good old positive 1. Alright, so bring down your 1. 1 times 1 is 1. Negative 8 plus 1 is actually negative 7. 1 times negative 7 is negative 7. 17 minus 7, that would give you 10. 1 times 10 is going to end up being 10. Negative 8 plus 10 is 2. 1 times 2 is 2, so 16 plus 2 is 18. Yep, we have a remainder of 18. That's definitely not going to work. Positive 1 doesn't work. Alright, so how about negative 1? Let's give that a try. So bring down the 1 from above. So negative 1 times 1 is negative 1. Negative 8 plus negative 1 is negative 9. Negative 1 times negative 9 is positive 9. Alright, so 17 plus 9 is 26. Negative 1 times 26 is negative 26. Negative 8 plus negative 26, that's negative 34. Negative 1 times negative 34 is positive 34. 16 plus 34 is 50. Well, we have a remainder of 50. That's definitely not going to work. So that means the 1's are out of the equation there. So we've narrowed down the players just a little bit. So we'll go to 2 next. Alright, so let's do positive 2. So bring down that 1 from above. 2 times 1 is 2. Alright, so negative 8 plus 2 is negative 6. 2 times negative 6 is going to end up being negative 12. 17 minus 12, that's 5. Alright, 2 times 5 is 10. Negative 8 plus 10 is 2. 2 times 2 is 4. 16 plus 4 is 20. We have a remainder of 20. That's still not going to work. Let's try negative 2. So bring down your 1 from above. Negative 2 times 1 is actually negative 2. Negative 8 minus 2 is negative 10. Negative 2 times negative 10 is positive 20. 17 plus 20 is going to be 37. Negative 2 times 37 is negative 74. Negative 8 minus 74 is negative 82. Negative 2 times negative 82 is positive 164. 16 plus 164 is 180. That's definitely not going to work. So you could take your 2's out also. We've narrowed down the playing field even more. Alright, let's try 4. Alright, so bring down your 1. Now 4 times 1 is going to end up being 4. Negative 8 plus 4 is negative 4. 4 times negative 4 is negative 16. 17 minus 16 is 1. 4 times 1 is 4. Negative 8 plus 4 is in fact negative 4. And then 4 times negative 4 is negative 16, and that gives you 16 minus 16 is 0. So we found one of our zeros. So let's write out the linear factorization we have so far. We have f of x would equal the quantity of x minus 4 times x to the third minus 4x squared plus x minus 4. Well, definitely have some good news here. This cubic factor can definitely factor as factoring by grouping. So this is going to break down into, let's see, we have x minus 4 on the outside of that cubic factor. Let's put some brackets here. So the x cubed minus 4x squared, that would have you x squared times x minus 4. Then you would just have plus x minus 4. So this is going to break down into x minus 4 times x minus 4 times x squared plus 1. Alright, so far we're at f of x actually would equal x minus 4 squared times x squared plus 1. So yes, you have a repeated x minus 4. You can make this x minus 4 squared. It only looks like one zero, but it's squared. It actually counts as two of your zeros. But your other factor is the sum of two squares. So this can factor further into f of x equals x minus 4 squared times x plus I times x minus I. That's your complete linear factorization for f of x. And then your solutions would be x equals 4 and then plus and minus I. It looks like we only have 3 zeros, but that 4 occurs twice, so that actually counts for 2 of your zeros. Then you have plus and minus I. So really, we've met the criteria of the fundamental theorem of algebra. We have 4 solutions in the complex number system. When you're factoring, you might square it, but if you're writing out what your solutions are, you only have to list that 0 one time. Now, if you were going to graph something like this, you would probably want to put 4, then in parentheses, multiplicity of 2, because then that would help you with the graphing behavior. But otherwise, this is plenty sufficient. So that's it for this lesson. Next lesson, we're going to move on to rational functions. So I hope everyone has a great day. Take care.